All right, so I want to introduce you to some ideas that discuss how to deal with complex differential equations. And these ideas come from the world of dynamical systems. There is an excellent book that if this stuff is interesting to you, I extremely highly recommend you buy that book, Strogat's Nonlinear Dynamics and Chaos. It is one of the few textbooks that I feel like you can sit down and read it, like as almost as if you were reading a nonfiction work or something. Like it actually is a readable book. It's in a sense conversational, but then also really deep and really clear in how it explains its concepts. I don't say that about many books. So I think if what we talk about today is of interest to you, track down that book and it'll be invaluable. So a lot of this comes down to things that we've skirted around a lot throughout the semester. And it's this idea of linearity. And this is a topic that we're going to revisit again when we talk about partial differential equations, because there are kind of more formal methods we can use to identify linear versus nonlinear systems. But for right now, we'll focus on ordinary differential equations. And we're going to return just for briefly to the ordinary differential equation that you've been staring at for the last 2 weeks, which is the one that describes a damped harmonic oscillator. So something that's like mx double dot plus a x dot plus kx equals 0. You derived this equation, you non-dimensionalized it, you did all the work to solve this. What we're going to do now is show how to kind of use a little trick from differential equations to rewrite this as a system of equations that turns out to be easier to work with and allows us to use different methods for understanding how this system behaves, or any system that is described by an ordinary differential equation of kind of n variables behaves. And the general framework requires us to think about a system of differential equations such that we can write a system of equations of x1 equals some function f1 of x1. And this could be including many terms. We can go all the way up to xn, which is got a different function, f of n, which also takes x of 1 to x of n. So the idea would be, can we write our differential equation in this form here? And you might be thinking, well, what just happened? The first thing you wrote down was a second order ODE, and you just showed me the general framework consisting only of first order ODEs. And the trick that's often used is to introduce a new variable, and let's allow us to write x1 as being what we've just considered x, and we can write x2 as the derivative of x. What does this mean? It means for us that we can say that x1 dot is equal to x2, and then x2 dot is equal to what we were initially thinking of as x double dot. And I'm just going to write this in kind of a dividing through by x. So I'll write negative a over m times x dot minus k over m times x. So all I've done here is I've gone to our original equation for the damped harmonic oscillator, moved the terms that don't involve x double dot to the right-hand side. And now, based on this definition of saying x1 dot is equal to x2, and x2 dot is equal to the second derivative of x, we can write this as like so. Why are we doing this? Well, we're doing this because as it turns out, it's easier to evaluate and characterize these equations if we can write them as a system of kind of first order ODEs instead of as one single second or third or fourth ODE. And the first thing we can do is we can very quickly ascertain whether or not this equation is linear or not. So how do we do that? Well, we look at the right-hand side. So we have two things. We have x1 dot and x2 dot. Now, just to recall, that's kind of like what's here. And on the right-hand side of each of those equations, we have some function of our variables. So right here, it's a function of x1, x2, x3. And this is exactly what we see. This is a function of x2. It's just equal to x2. And over here, we have, this is some constant times x2 minus some constant times x1. So immediately what we can do is we can determine that this system of equations is linear. And how do we do that? It's linear because on the right-hand side of both of these equations, x to the I on the right-hand side appear only to the first power. Let me move that over. So this system here is linear. Oops, I don't want to do that. Let me do it over here. It would be nonlinear if on the right-hand side it contained terms that included, for instance, products of x1 and x2, maybe x1 cubed, maybe the cosine of one of the things, so like x2, and so on and so forth. Anything that's not simply x1, x2, x3, x4 to the first order. Why do we care about nonlinearity? We care because linear systems can be broken down into parts, and then you can solve each part separately and then combine them together to get the solution. Linear systems are quite literally equal to the sum of their parts. This concept and this simplification, or I guess this not simplification, this kind of feature of linear systems underscores many of the familiar mathematical methods you might have encountered in the past, things like Fourier analysis, Laplace transforms, superposition principles, normal mode analysis. All of these things allow you to kind of break up something into parts and then add them, all those solutions to those little parts up to arrive at the full solution. However, in most things in the world, most things that you'll model are nonlinear systems. Effects from one thing contribute to the effects of the other and have a completely different behavior on the outcome, and they don't simply just add up. For nonlinear systems, the concept of superposition fails miserably. You might think that pickles taste delicious, and you might think that ice cream also tastes delicious, but if you eat pickles on top of ice cream, that does not mean you'll get twice the amount of enjoyment out of your meal. That's a silly example, but it's kind of true for all of this stuff. Like this concept of finding the outcome of one particular component and another particular component and summing them together only works with linear systems. Nonlinear systems are really difficult to evaluate, and in many cases really difficult to generate solutions, or even simply proof that a solution exists, and if that solution exists, proof that a unique solution exists, that there's only one. However, there's some tools that we can use to start evaluating these things. So here's a nonlinear system. This is another system that we've kind of looked at in gory detail from time to time. And it is that x double dot plus some constant times the sine of x equals 0. In the dynamical systems world, if lambda is kind of g over L, we get something that describes a pendulum. If lambda is something like P over B, then we get something that describes the elastica. Both of these systems are nonlinear. We can still write this into our framework that we've just introduced, and we can confirm this is nonlinear by simply saying that we'll let x1 dot be x2, and we'll let x2 dot be, again, go to our equation for the pendulum, move the terms not involving x double dot to the right-hand side, and we get x2. So it'll be negative lambda sine x1. So immediately you can see the appearance of this sine x1 term on the right-hand side, and you know immediately this is a nonlinear system. So what we're going to do is we're going to look at some geometric methods for evaluating systems of ordinary differential equations, and we're going to see that we can learn a lot about them without ever solving the equations at all. So the idea is, suppose we know the solution for instance, this pendulum problem, given for a particular initial condition. Like, for instance, we could linearize the system and say that the small angle approximation holds, and so we might be able to solve what's happening for the pendulum as long as the initial angle is not very large. That solution that we're going to get is going to give you a pair of functions. It's going to give you, so for instance, in the case that we've written down so far for the pendulum, we only have x1 and x2. It's going to give you the x1, it's going to give you a solution for x1 of t and a solution for x2 of t. In this sense, we can kind of think of these terms as, you know, this is effectively like a position of the pendulum, maybe position dictated by an angle or about the origin, and this would be something that's like a velocity. And what we would do is we'd want to plot this in an abstract space that allows us to produce what's known as a phase portrait. So what does this look like? So this phase portrait, in the case where we only have these two systems, might be like x1, x2. So the x-axis is our position, the y-axis is our velocity. And you can imagine that, you know, to solve this differential equation, we're going to need to give it some initial condition. So for instance, we're going to need to say that x1 at time 0, comma x2 at time 0. So the initial position and velocity of the pendulum would set off some motion. That motion is going to follow some trajectory in this space. So maybe it'll do this. I'm just drawing something here. It's arbitrary. Kind of put some arrows along here. So this line that I'm drawing is what's referred to as a trajectory. This plot that I'm drawing here is our phase space or phase portrait. And if I was to look at, for instance, some point along here, that would tell me what the position of the pendulum and the velocity of the pendulum is at some point in time t that we might be interested in. Now, we should be able to imagine that we could completely fill this phase space with trajectories. And each point could serve as an initial condition to our pendulum. So we could start here and see what happens to the velocity and position over time. We could start here and so on and so forth. What we want to do is do this in reverse. We want to use geometric methods to help us draw trajectories without solving the equations. But by doing so, we're going to be able to extract information about these solutions. Let me give you an example. We're going to return to the pendulum, but let me start with something simpler. So we're going to start by thinking about differential equations as vector fields. That sounds more intimidating than it is. Let's consider the following differential equation. Something simple. It's x dot equals the sine of x, and x at 0 equals some initial position. We know this is nonlinear. It actually happens to be one of the few nonlinear equations you can solve exactly. I'm going to use NL to abbreviate nonlinear. We can solve this exactly by separation of variables. What we would do is we would say something like dt is equal to dx over sine of x, separation of variables, and then we can integrate to find that t is the integral of the cosecant of x dx. And inputting our boundary conditions, or sorry, our initial condition, we can resolve that the solution for t is the natural log of the absolute value of the cosecant of x naught plus the cosecant, oops, sorry, nope, plus the cotangent, can't read my writing, of x naught over the exact same thing for x. Cosecant x plus cotangent x. We have a solution to our equation, but this solution doesn't provide us with a ton of clarity or understanding. So for instance, so say I ask you, I'm going to tell you that x naught is equal to pi over 4. Describe how the solution changes as time increases and tends towards infinity. It's not really that clear to look at this just awful solution of cosecants, cotangents, and a natural log to be able to evaluate what's happening in that specific case. And it's certainly even harder if I was to ask you a question like, imagine I give you any arbitrary choice of x naught. What's going to happen to x of t as time evolves? We're going to do this graphically to illustrate how we can use geometric methods to give us qualitative understandings of our dynamical system. So instead of solving this equation, like pretending we can't solve the equation, maybe there's not a solution that exists. So what we're going to do is we're going to plot this equation in our phase space. So I'm going to do this a little bit bigger here. We're going to say that, oh, that was terrible. So on our x and y axis, our x axis will be x1, which for simplicity, just to remind you, is just going to be x here. And our y axis is going to be x2. And again, this is going to be x dot. And so what that means is what we're plotting is really just what I highlighted in orange there, sine of x. So let me see if I can draw a sine curve that's not too ugly. Pretty ugly. Okay, we can live with that. Okay. Does everybody understand what I just plotted? I'm literally just plotting the sine of x. Question? Okay. What we're going to do is we're going to say that if we think about this as a particle moving with a velocity, then we know that if the velocity is positive, the particle should move forward. And if the velocity is negative, the particle should move backwards. So the velocity here corresponds to the y-axis. So when the y-axis is positive, we would expect our particle to move to the right. And we're going to illustrate that by adding a little vector here. So everywhere from here to here, the particle is going to move to the right because the velocity is all above the x-axis. Now over here, we're going to say that our velocity is going to move to the left. Sorry, our velocity is negative, so our particle is going to move to the left. And again, over here, we're going to say our velocity is positive, so it's going to move to the right. Over here, negative, so it's going to move to the left. Over here, it's positive, so it's going to move to the right. So we're adding vectors to describe the way the particle will move simply by saying positive velocity means moving to the right, negative velocity means moving to the left. Now what you notice is that there are these kind of fixed points or critical points at which the velocity changes signs, where you cross the x-axis. When arrows point towards a critical point or a fixed point, we're going to just say that that fixed point is stable. Actually, I'm going to use a different color there. Sorry. I'm going to use red. There we go. We'll say that that fixed point there is stable. Any particle that kind of starts over here or over here is going to move to that point. And then it's going to stay there. Any particle that starts near this point is going to move away from it. So if it starts slightly to the right of this point, it's going to move to the right. If it starts slightly to the left of this point, it's going to move to the left. So this is a fixed point, but it's unstable. So I'll draw that with an open circle. So stable, unstable, stable, unstable, stable, unstable. Let me just mark these so that you see. So this is stable. This is unstable. We often refer to these stable fixed points depending on what system, what world you're operating in. This might be called a sink or an attractor. And these unstable points are often called the source because that's where kind of things come from, or a repeller. So now you know, given a starting position, what the particle is going to do. Before I demonstrate this, is everyone comfortable with how I've marked the vector fields and how I've denoted the fixed points? So now we can go back to our initial question that I said out loud, which is, well, what happens if a particle starts at x naught equals pi over 4? Well, now we can know, because look, let's see here. So this is pi. This is pi over 2. Pi over 4 is going to be somewhere over here. So if a particle starts at pi over 4, it's going to very quickly move to the right with a kind of an increasing velocity. So it's going to basically accelerate up till about pi over 2. And then it's going to start to kind of decelerate and approach this stable fixed point. And as time goes towards infinity, it's going to approach pi ever slowly and kind of stay there. We can graph this. We can say, let's look at what we want, which is what is x as a function of time. So if we said that x is going to start at pi over 4, just arbitrarily, it's going to rapidly accelerate and then kind of slowly and asymptotically approach a value of pi. This is qualitative. I'm hand sketching that curve based on what we just said by looking at the trajectory in our phase portrait. Does everyone see this? And does this make sense? It's okay if it doesn't. It may be very unfamiliar. So we now know how to qualitatively evaluate this particular starting point. But we actually know a lot more than that, because now we can say, well, let's look at any arbitrary x naught. If my particle starts where its velocity is positive, it's going to move to the right until it approaches the nearest stable point, stable fixed point. If my particle starts with a negative velocity, it's going to move to the left until it approaches the nearest stable fixed point. If my velocity is initially 0, it doesn't move at all. We can actually sketch all of these solutions on one master curve if we want. So my stable fixed points occur at pi and 2 pi. And as well at negative pi and negative 2 pi. And I could just pick arbitrarily a bunch of different curves where I could start at. And if I start, we can go for the pi over 4 case. If I kind of start somewhere over here, I'm going to accelerate and then slowly approach my stable fixed point. If I start over here, I'll kind of pass pi over 2, and I'll be just decelerating and approaching my stable fixed point, moving in the positive direction. If I start to the right of a fixed point, I'll move to the left. This curve should be kind of symmetric, the same as the last one I just drew, and the same as before. If I start close to pi over 2, I'm going to do something like that. Oops. And I'll pretend that gets closer to pi. I guess let me draw pi in there. And I can do this again for down below as well. So we have now been able to sketch the qualitative behavior of our system for any arbitrary starting point just by using these graphical methods. Questions?
Professor?
Yep.
What are we defining what happens when we start exactly at a source?
Nothing happens. It stays there. Now, okay. That's the same as saying that you can balance a ball on the top of a very steep hill. There's nothing about mechanical equilibrium that says that's not possible. You can absolutely balance your forces there. But as we know, any slight perturbation would, as soon as that thing gets anywhere off of that fixed point or that equilibrium point, it's going to move and go towards the next stable fixed point. So in reality, things don't kind of start at exactly 0, or if they do, they might not stay there forever. And what happens is any tiny perturbation will kind of knock these things from one starting point off. And that's actually what dictates stability. We're going to come back to this in a little bit, is that's how we can think about stability, because the idea being, if I'm at a stable equilibrium point, if I have my ball and I'm at the bottom of a bowl, I could perturb that thing. I can just push it to the side, and we know it's just going to kind of slowly come back and rest and stay at that equilibrium point again. That's what we mean when we say that equilibrium point is stable. And so your question about if you start at a source is a good one. If you have a perfect system, there's no possible chance for any stochastic noise or anything that's going to constantly perturb it. It'll stay there forever. Now, in the real world, that doesn't really happen.
Thank you.
Other questions? I want to try something. I want to show you a complex phase plot, and I want to see if you can interpret the results. So, let's see what I can do here. This might seem arbitrary, but it turns out our friend Mathematica makes it incredibly easy for us to plot phase portraits. So here's our pendulum equation. Here is our pendulum equation written in kind of as a system of first order ODEs. And Mathematica has a function called stream plot, which will generate the phase portraits kind of over the entire system, or whatever domain you want. Now again, your x2 is kind of, your y-axis is kind of like your velocity, and your x-axis is kind of like your position at any point in time. And so what I'd like you to do, hopefully you can see this well, is stare at this for a minute and see if you can understand. Can you identify where the stable fixed points are and where the unstable ones are? I couldn't mark them with open circles, so they're just all circles, but you have to figure out which one's which. And then this is the model for a pendulum. So what I'd like you to do is to see if you can think about what it means to start at any one location on this phase portrait. So take a few minutes and stare at this. If you've already done this before, then take a breather. But if not, see if you can understand the entire possible range of dynamics of a pendulum that is in this one plot here. Have you seen this stuff before?
Yeah, I took Nonlinear.
Okay,
cool. So
Yeah, I know some people have. I just never tell if everyone has.
it's a easier way to look at it than what I've done before. But I don't know. I mean, obviously it's not as in depth, so I don't know if it's quite as meaningful, but it's definitely like easier to understand.
Yeah.
The way they usually teach is very high level.
Yeah. Okay, who wants to say anything about this face portrait? What does it mean if I was to say, let's start here?
It's gonna spin.
Not quite.
Oh, wait.
All right, let me ask you this question even more basic. Is this a stable or unstable fixed point? It's perhaps easier to think about these ones out here. Thinking about the terminology we used for these unstable fixed points being repellers or sources.
Yeah.
So out here, these are our unstable fixed points. You can kind of see that because the trajectories approach it and then go away from it. The trajectories approach this unstable fixed point and then they move away from it. Over here, they kind of just hang out around this fixed point kind of forever. You could think about that if you'd like as an orbit. So now think about what are the possibilities for a pendulum. What's the unstable point of a pendulum?
Top of it when it's straight up.
Yeah, what was said in class here is that the unstable configuration of a pendulum is when it starts upside down. Now it could technically stay here forever, but any slight perturbation will cause this to fall down. The stable position of a pendulum is simple, right? It's just not moving, right? This is the stable configuration of a pendulum. If you were to turn on some sort of, I mean, this is kind of where it's happy. This is also an equilibrium point, and it's where it's unhappy. I'm getting a lot of silence. So if this is the stable fixed point, which corresponds to this configuration, then being slightly away from that thing in position corresponds to it being slightly away from being vertical. And now what do you think this tells you it's going to do? It's going to keep switching velocities, positive velocity, negative velocity, positive velocity, negative velocity, positive velocity, negative. Let's see if I can match this. Just like to pat your head in the belly at the same time or something. If I start a little bit further away, so I perturb this thing even further, maybe I'm out here, it's going to do exactly the same thing, except the only thing it's going to do is its amplitude is going to be bigger. The amplitude being kind of like the distance between here and here. So now I start here and I'm going to sway back and forth, positive velocity, negative velocity, positive velocity, negative velocity. I can get really fast. This is now I'm pushing my kid on the swing and he wants me to keep going and he's really worried he's going to flip over, but he's not going to flip over. And now I push so fast that the pendulum goes up, approaches this unstable point, and it comes back down. And that's like really out towards this outer edge here. I'm almost at the vertical, and then I come back down, and I go vertical. Now, what about these streamlines up here? What do they correspond to?
Isn't that like going round and round and round?
Yeah, exactly. That's going to be when you're just kind of spinning crazy fast. And you never get near this stable point because you're going so fast that you never even kind of see that this stable point exists, and you just kind of spin around and around. So increasing and decreasing. So now you can kind of drop in a particle at any point on here and immediately know what that particle is going to do. I imagine that there's someone sitting there thinking, I don't understand why these orbits are circular and not spirals. Like if I start here, why does it do this? And why does it not just kind of do that? Anyone know the answer?
You don't have any damping effect on it.
Yeah, exactly. There's no damping in our system. There's no friction. There's no anything to dissipate energy. So it's just going to happily do that forever. Now we know that's not physically real. There is damping or viscosity or something that's going to dissipate that energy, and it's going to eventually come down and stop. But we don't have that in our equation. So it's basically saying, well, in the absence of anything like that, it's just going to do this forever. I don't know how to interpret your silence, so please bring questions to me.
You don't have a demo plot with the damping in it, do you?
No, I actually started trying to make one last night, and then I was like, what am I doing? I have to let's move on. Not yet. But I think that's something I will play with. Yeah.
Really cool.
Yeah. I actually was working on putting like points in there and animating them, and I was like, this is crazy. It's too much work. Anyone? Bueller?
If we did model the like friction or damping, I guess, what would the top lines look like?
They won't change that much. Unless the damping is so strong that it starts to pull you into that center orbit. And so like as the damping increases, if you're kind of spinning, at some point you're eventually going to get kind of sucked into towards that stable orbit, and it'll dissipate out towards kind of stopping.
Okay.
But once they're really far away, it's going to take a really long time for enough energy to be dissipated that they kind of fall to the next level spinning, 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 fall to the next level, spinning slower, 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 fall. Because remember, the y-axis here is velocity. So higher up means you're going faster. So as you come down, it means you're going slower. And eventually, if you go slow enough, you'll kind of get sucked in towards this other stable orbit and then continue slowing down and dissipating.
Okay.
Does that make sense?
Yeah, definitely.
Other questions? All right, how about this? How about I give you a couple-minute break and we'll come back and you can fire questions at me either in the break or when you get back. All right, we'll recover around here at like 12:10.
You can find some pictures of the damp one online
Oh, nice. Okay.
where you can see it sort of when it drags it out, it kind of they fall to the next still point.
Yeah, I gotta figure out how to draw those. That's super cool. Thought this would be more exciting. I think it's pretty cool.
I like it.
I mean, we basically solved the whole nonlinear system without even doing anything. Just plot it.
It's funny when you get into like the three-dimensional things where you get the like saddles and stuff.
Yeah. All those crazy manifolds or stuff can kind of roll off in different directions or roll toward you.
If you had more, I don't really remember doing it, but if you had more like x1, x2, like replace variables, how would you look at it up through like past 3, I guess?
Yeah. I mean, the answer is pretty much always not with 3D plots. I mean, like, they're kind of cool, but
They don't tell you a lot.
no, they don't. So usually what you do if you have more than 2 parameters is you start creating phase portraits at fixed parameter spaces for the other one. And so you start kind of creating like these portraits where like if x3 is this, then here's what x1, x2 looks like. If x4 is this, here's what x2. And then usually you have to kind of help it along with a bit of like physical insight in terms of like, okay, having this thing fixed is equivalent to I don't know, taking like setting the friction for this particular value, and at this particular value, this is what the system would look like. And now we're gonna like vary the friction, and you can look at plots for as the damping increases. That's almost always a bad idea to plot 3D things. And
Yeah, that I definitely.
yeah, and in general, what you want to do is like figure out what you can fix and what you want to vary. All right, let's get back. So not many questions emerged. I don't know if this is because it's too familiar, because you've seen this in controls courses or dynamical systems courses, or if it's too unfamiliar and you're just kind of confused with what all these arrows mean. So let me know. But I think it goes without saying, whether or not you're confused or whether or not this is very familiar to you, this is pretty impressive. And we took a nonlinear system that's incredibly hard to solve. It has to be solved using the theory of elliptic integrals, which are very complex. And we understand all of the quantitative behavior of the entire system for any given set of initial conditions with just plotting our system in this phase portrait way and starting to evaluate what these curves mean. I think that's really powerful. Let me do another example that's maybe somewhere in between what we started with and the phase portrait of the pendulum. So let's look at, as an example, a problem involving population growth. The simplest model for population growth dates back to the late 1800s. And the simplest model assumes that there's some rate of change of the number, or like in the population of, say, organisms, that is going to be dictated by the growth rate and the number of times the number of organisms. So, for instance, this means this is the number of organisms at time t. R here is your growth rate. And this describes the rate of change of that growth rate. So this is a straightforward ODE that you know how to solve. Whenever you have something that says the derivative of your thing is equal to your thing, then you know that you're going to have something that yields an exponential solution. We interpret that in this case as meaning there would be exponential growth. Now we know that that's not the case. We know that just kind of conceptually we can say, well, if a population continues to grow exponentially, there's going to be overcrowding, there's going to be a limitation of the number of resources available. So there's going to be some kind of maximum capacity that can exist, or the maximum number of organisms that can exist. We'll call that the carrying capacity. And the idea is to say that we have to add to this model the idea that the growth rate, which is n dot over n, will decrease when the number of organisms exceeds the carrying capacity. K is just a number. So the maximum number that we can have. And the simplest way to add this kind of physics, if you will, or concept into our model is to assume that R, which is equal to n dot over n, decreases linearly with n, once we exceed the carrying capacity. Or I guess just in general, you could say that I should say it a different way. R, the growth rate, is not a constant. It depends on n, and it'll decrease linearly with n. So there's two ingredients to this model. One is n dot should increase exponentially, but R should decrease linearly with n. This leads to a very famous equation. So if you combine these two things together, you end up with what is referred to as the logistic equation. The logistic equation looks like n dot is equal to Rn times 1 minus n over k. So it's just kind of the first part, and then accounting for the fact that we have a linear decrease as n increases. We can plot this without solving it. We can just plot n dot as a function of n. And what we'll get is a curve that looks like this. And that point at which it crosses the x-axis is at k. This just amounts to literally plotting the right-hand side of this thing here. So it's just, all I've done is just, you can just go into Mathematica yourself and plot this, give it a particular value for R, give it a particular value for K, doesn't really matter. You're going to get the same shape curve every time. It's going to be the one I plotted. Your numbers are just going to scale. So you're just going to kind of stretch that curve. Okay, let's use our graphical methods to describe what's happening here. So we know that when the kind of velocity, if you will, the rate of change of our thing is positive, then we expect our system to move to the right. And then when our rate of change is negative, we expect our system to move to the left. That means that point K is our stable fixed point, our stable equilibrium. Conceptually, what this means is that a population of organisms growing, if you have a couple of organisms lying around, they're going to exponentially grow up until you get to some point that is, turns out, about k over 2, actually exactly k over 2, at which point the growth rate is going to start to decline. You're going to still be growing in population, but you're just going to grow slower and slower and slower until you asymptotically approach the carrying capacity K. This point here is an unstable equilibrium point. It gets back to Reese's question. Obviously, if there are 0 organisms, there's going to be 0 population growth and you'll stay there forever. Any slight perturbation away from 0, I guess perhaps 2, you will start to exponentially grow and you'll go in that one-way direction. This is a one-way phenomenon. There's no really way to conceptualize what a negative population is. So this is just going to go to the right. And we can sketch our curves really quickly. So we can say, well, hey, okay, let's look at, just like we did for the first system, let's look at some different scenarios. So imagine we start, so we want to solve n as a function of t. We didn't solve this differential equation at all. I'm just simply going to sketch what I think is going to happen. If I start near 0, I'm going to exponentially increase until I get to k over 2. And then I'll start to kind of slow down my increase and asymptotically approach k. If I start above k over 2, then I'll just kind of slowly increase my population until I get to k. And if I start greater than k, I don't really have a growth rate anymore. I have more of a death rate where deaths are outnumbering kind of births, if you will. And I'll slowly decay until I get to the stable fixed point here. So we can sketch that. We can say, well, let's call our stable fixed point is k. It's just a number. And therefore, if we start near 0, but slightly more than 0, we're going to get something that's like this. This curve is kind of S-shaped, and it has the term, it's a sigmoid. If I start above k over 2, then I will just kind of slowly increase until I approach my steady state value. And if I start above k, then I'm going to exponentially decrease and asymptotically approach my k. I want to emphasize, we did no calculus. We simply plotted our equation as a vector field, and then using how that vector field is what is telling us, so in terms of the direction that things will move and the rate that things will move based on the slope of this, then we can sketch out the population as a function of time, these qualitative solutions for kind of any arbitrary starting point. You either kind of exponentially grow and then plateau, slowly grow and then plateau, or exponentially decay and then plateau. In the sake of full disclosure, this model works pretty well for modeling really simple organisms, bacteria, yeast, very simple organisms in which there's no predator or predator-prey modeling. There is a constant supply of fixed food source and constant climate. And it works really poorly when you deal with more complex systems that have kind of all those additional variables that lead to competition and such. But I'm just emphasizing, so far, we've looked at 3 different systems governed by differential equations. We've sketched their solutions by sketching their phase portrait. And we've obtained the qualitative behavior of these systems without doing any math whatsoever. And that extended to what we did when we looked at the phase portrait of the pendulum. You know, we were able to kind of qualitatively describe that behavior without solving that equation quantitatively at all. Questions? Is this making sense? Is this not making sense?
This is making sense, but one thing I'm thinking about, so our solutions are not symmetric about our stable point like they were before, and that's because our phase plot is not symmetric about the horizontal axis. Am I understanding that right?
Yeah, that's fair
makes
to
sense.
say. I mean, we started with the most kind of symmetric system. We had that sine curve in which we had, harmonic behavior. So symmetry in time and symmetry in space. So there's a ton of symmetry in that plot. And so all of these things are kind of led to symmetric behavior. But exactly, we don't have symmetric behavior about kind of reflecting about n dot equals 0. And so therefore, when we evaluate our solutions, we're not going to have symmetric, or let me say, yeah, symmetric is accurate, but we're not going to have the same type of behavior of our system depending on where we start with x naught, because the behavior, there's kind of 3 regimes to this system. Whereas in the last case, there was really kind of maybe 2 regimes and then symmetries about those regimes due to the nature of the differential equation.
Yeah, that makes sense. Okay, cool. Thanks.
Other questions or comments? I'm sure there are some of you who are kind of uneasy about the lack of quantitative information that we're extracting from this. there are some quantitative features that we can extract, especially about the nature of these fixed points. We can determine the stability of these fixed points quantitatively without relying on graphical methods. And the way to determine the stability of fixed points is by using what's referred to as linear stability analysis. And this is simply just the mathematical way of implementing the thought experiment I had you do, which is to say, go to a fixed point, perturb your position, and see if you return to the fixed point. Okay, well, how do you do that? Well, we know, so we're going to have to linearize about our fixed point. We'll call our fixed points x star. So we'll call it like that. So we want to first make a perturbation about our fixed point. And luckily, we've spent a lot of time thinking about perturbations, and it's exactly the same. So we're going to perturb around, oops. And the way we perturb around x star is we introduce the exact same function we introduced when we're dealing with calculus variations, which is eta of t in this case, which is going to be equal to our position some distance away from our fixed point. Remember, when we introduced calculus variations, we kind of had the curve that was the exact curve, and then we had our pretend curve that we perturbed, and we had a vertical distance between those curves at every point t, and that vertical distance between those two curves at every point t, we called eta. Same exact idea. We want to determine if our perturbation grows exponentially or decays exponentially in time. So we're going to take our system, our pendulum, we're going to perturb it about the fixed point, and what we want to know is, does this thing decay over time? Or does this thing grow over time? An easier way to think about growing is, if we're at this stable fixed point, the perturbation is really small, but over time, that perturbation is going to grow because that thing is going to move away from that stable fixed point. So we want to understand the rate of change of our perturbation. How does our perturbation change in time? Does it grow in time or does it decay in time? To determine how our perturbation changes in time, we take the derivative of our perturbation with respect to t. Let me write that down. So now we need to evaluate the derivative of eta. Now this is pretty simple because x star is a fixed point, it's a constant. So therefore, eta dot is equal to x dot. Now if you recall, x dot here is just our function. So x dot is my y. Oh boy, hold on. There we go. X dot is my function. It's y of x here. My function is y of x. What I'm plotting here is sine of x. So x dot, the way we parameterize our system of ODEs, x dot is simply the function that we're interested in. So it's f of x, some arbitrary function that we are interested in studying. Above it was sine theta. In this example, it was Rn, all of this stuff, the logistic equation. And so I guess I skipped a step here. Hold on a second. Let me do this really quickly for you so it's all clear. You can keep that written down if you wrote it. I just want to, what we're really saying is we're going to take the time derivative of this And that's going to just simply equal x. X dot is equal to our function that we've been studying. That's what we've been plotting. We've been plotting x dot versus x dot being the function. And so therefore, we can think of our function as the fixed point plus our perturbation. So what we want to do is evaluate how our perturbation changes in time. So we differentiate it. And then we look at that perturbation around the fixed point. So f, our function of the fixed point plus our perturbation. And now, so let's summarize this. So simply eta dot is equal to f of x star, so my fixed point, plus my perturbation. So far, all we've done is set up our ability to examine how our perturbation changes. In order to do that, we need to next linearize. This is the crucial component of this linear stability analysis. And the way we linearize this is also familiar to us. It's the same stuff we've been doing. We linearize this by expanding it in the Taylor series. So we say that f of x star plus eta. If we expand this about eta being equal to 0, then we would get that it's equal to f of x star plus eta times f prime of x star plus some higher order terms. Now, if we look up here, this first term here is the function evaluated at the fixed point. The fixed point is defined as when the function is equal to 0. So here's a fixed point, this red dot. Here are fixed points, these red dots in the red circle, open circles. So by definition, this is 0. And as long as the term before it, oops. As long as that derivative term here, oops, is not equal to 0, then we could ignore all these higher order terms. So what we're left with is an equation that says eta dot is equal to eta f prime of x star. Now again, this is simply going to yield an exponential solution. Eta dot, the derivative of eta is equal to eta times something. And so the only way that's true is if we have our function be exponential. But now look, this actually tells us something. It tells us that our perturbation will grow exponentially if the derivative at the fixed point is positive. This corresponds to an unstable fixed point. And it will decay exponentially if our slope is negative. This corresponds to a stable fixed point. Now let's scroll up and evaluate, look at what we've done. It's telling us that as long as the slope is negative, our fixed point is stable. Well, look. Slope is negative, stable fixed point. Slope is positive, unstable. Slope is negative, stable. Slope is positive, unstable. I think that's all I have. This is true for any arbitrary function that you can plot using these geometric methods. The slope of our function near the fixed point dictates its stability. If that slope is negative, that's a stable fixed point. If it's positive, it's unstable. And you can prove that by implementing linear stability analysis. So it allows you to just look at the derivative of your function at the fixed point and just simply evaluate its sign. And it'll tell you if you're looking at a stable or unstable fixed point. You can actually do a little bit better because the sign dictates stability. The magnitude of that slope determines how stable or unstable that fixed point is. If that slope is really, really steep away from an unstable fixed point, you know that that particle is going to move away exponentially very, very fast, rather than if it's incredibly shallow and almost near zero. So much so that you actually, at least in the case of a dynamical system where this is all leading to time scale, derivatives with respect to time, you can actually determine a characteristic time scale which is going to be, let's say, call it tau, and it's equal to 1 over the absolute value of the slope evaluated at x star. This gives you the time required for x of t to vary significantly near that fixed point, kind of like the duration it takes before that thing will move rapidly away from it or rapidly towards it. So you actually can ascertain quantitative information from these systems, and depending on how the questions you're asking. These questions of stability and points of stability are some of the most fundamentally important questions that you're looking for in these complex nonlinear dynamical systems. Think about the Euler buckling problem you encountered in like a mechanics of materials problem. The main thing you solve for is, well, at what point will this thing buckle? You kind of are happy to lose information about like, oh, when it buckles, what's the shape of the thing? You often are just interested in like, when will it buckle? Under what loading criteria will this thing buckle? And so oftentimes these kind of qualitative features that signify a change in the behavior of your system are really what you're trying to quantify when you're looking at these complex nonlinear problems. All right, I've thrown a lot at you today. I don't have any sense of if this is really making sense or if it's familiar or not. So we have a few minutes. How can I help? How is this sitting with you all?
How can this linear stability analysis apply to the vector field that we found in Mathematica? Because these graphs that we're writing down in the notes are pretty simple, like one-dimensional vector fields, but the one that you have in Mathematica is two-dimensional. So it seems like it's not quite as simple as just finding a positive slope and a negative slope about the fixed points.
Yeah, what you're going to end up with here is instead of a line, you're looking at more of, let me share this really quickly. Instead of a line for these two-dimensional systems, what you're typically looking at is like a manifold, a surface. And you could think of this the stable surface as like a well. And now the slopes are going to be all negative, kind of axisymmetrically about that well. And that kind of well, these things are kind of, if you have imagine at the center here, this is like the center of a bowl. And what you have here is that different orbits correspond to kind of like different locations up the bowl. And they're kind of spinning around that location. Maybe they're spinning higher up the bowl, maybe they're spinning less high around the bowl. Now, in all of those cases, the kind of the slope here, as you were to evaluate it at different points, is all going to be negative. But now you're looking at the slope of a manifold. So what you might do is kind of take a cross-sectional cut and say, okay, well, how's the slope, at this point, to give you a sense of what's happening in that manifold. Now, the same is going to be true as you move outward to the unstable fixed points. That bowl kind of goes from being a bowl to being maybe a bowl with like a ridge, like an inverted, like a bowl with like a rim on the outside of it. And now that rim is kind of going to give you something that is going to be kind of positively sloped wherever you're encountering it. And so then at that point, that is going to signify that anything that's up there could kind of roll off of it. So you can kind of think of it as like, instead of it as a line, you really have more of like a manifold in which you have kind of a bowl for your stable fixed points and then hills for your unstable fixed points. But that idea of the slope around those fixed points being negative for stable, positive for unstable is still true. What you often have to do is look at that manifold and evaluate the slopes, for instance, in the principal directions of that manifold. And say, okay, well, as long as if I'm coming from this way, the slope's negative, so it's stable. What happens if I'm coming from this way? And if it's a bowl, it's still going to be the same shape, so you're going to be fine. But there are complex situations where there's more degrees of freedom, where kind of perturbing it this way is stable, but perturbing it this way is unstable, and you get these kind of saddle-like geometries and more complex kind of manifolds there. So the concept that we just said remains the same, but its interpretation has to be thought of instead of on a line, maybe on a surface, or maybe a stack of surfaces. And so the concept that we see in this linear stability analysis doesn't change, but kind of the slopes you're looking at does, and you might have to evaluate that slope along principal directions to check for stability. And that's what you're really doing, is checking for stability in regards to perturbations kind of coming from kind of different principal components, if you will. Does that make sense? I could try to find a way to draw this as like a manifold. I'll try to do that, so you can kind of actually like see that surface shape, because that can be helpful. It's often easier, and I didn't get a chance to, I ran out of time, but and I'll probably do this at the beginning of next class. It's often easier for us as engineers to think about potentials and potential energies and kind of wells, potential wells, and that arises naturally from us saying like, hey, I know what the potential energy of my system is. And that potential energy is oftentimes like a manifold, and you're kind of trying to see if you're basically saying, well, the ball is going to roll to the lowest point in this manifold. And so you can connect that same idea of potentials and manifolds to these dynamical system approaches and I can show you how to. I'll show you how to do that next class. But that same idea applies. Of you really have this surface where kind of wells in the surface dictate stable points, local minima, and bumps dictate like local maxima. All right.
That makes
What's
more
that?
sense.
Go ahead. All right, we are out of time, but we'll return on Tuesday and talk some more about how to evaluate these types of nonlinear systems qualitatively. And hopefully this is useful and helpful. Thanks, everyone.